And so this guy are the composite scalar. They're formed from their composite scalars. They're intrinsic wave functions. They evolve progressively involving 1, 2, 3 correlated quasi-electrons. They carry no information about the location of the plane because they're scalars. And this is the cluster-cluster correlation. It's entirely responsible for the positioning in the plane and it's blind to the internal structure of these guys. And then you need this A is required for symmetry over the exchange of particles among your clusters. It's not needed for the Laughlin wave function because there's only one particle in each cluster, but it is in general. So what are the correlation functions? The correlation functions are really simple. They're just the dot products of Z1, Z2, or if you have two particles in a cluster, Z12.Z34, Z123.Z34. They're just these various products symmetrized over all possible pairings. So it tells you that one particle from one cluster always talks to exactly one particle in their other cluster. That's the structure. Corresponds effectively to shells that have unit 1/2, 1/3, 1/4 filling. There's a simple recursion relation. I think this is the basic idea of the hierarchy, that you can build up the wave function for the next state that you want to form. If you're working on the 2/5 state, you want to build a 3/7 state, then you act on it. You do that by the shift operator is just a simple aligned product of the shift operator you used before with another, and that same property continues to exist with the corresponding scalars. What are the scalars? The scalars are these original quasi-electrons that we introduced in this first form of the wave function before we formed the composite fermions, and you just fill a closed shell full of these spinners. So this is a scalar because it's a closed shell. And you can go ahead and then work out the recursion relation for that, and it's really simple. The scalar that you're forming for the next filling corresponds to the scalar that you had in initial filling. You add one composite fermion of the new type, and then you operate with this aligned derivatives to take all the old quasi-particles, break one more pair, and make them of the new type. There's a simple recursion relation for this as well. So you can do lots of neat things with these. I'll try to hurry up here. Maybe I'll skip this, but you can do things like now in general construct the fractional charges for any of the wave functions. You can improve wave functions in the hierarchical form. You just put out little things in the plane and replace them with the replacement. So it's the first step of really beginning to execute this program like an effective theory. You can now match to experiment to figure out what that clipping ought to be. And you can construct open shell solutions that are really pretty. Like we figured out the one for 4/11th, and I think there's several others that we can construct. But I won't talk about that. I want to say a little bit about the half-closed shell because it's got us really intrigued right now thinking about this. So we talked about these trajectories through this LS plane where you keep either L fixed or S fixed. What if you don't? What if you form another trajectory with fixed filling where you have L equal to S plus a constant? These all converge to nu equal 1/2. There's a bunch of trajectories that go in that direction. And so look at the LS trajectory. It has some really interesting properties. First of all, what's the wave function look like? It looks like this. As you increase L and S simultaneously, you're increasing the number of shells. The filling of the shell stays fixed. And so you discover that when you get to the half-filled shell, large n, you have the square root of n quasi-electron types situated in these different shells, and average occupancy of each shell up to the square root of n. And if you go ahead and map it into its hierarchical form, then there are the square root of n scalars, and each one contains the square root of n quasi-electrons. So a really simple form. What's neat about this, and my day job is doing neutrino physics, is that if you look at the symmetry of this, that there's an exact symmetry then between exchange of the particle creation and flux creation of this, because they have the same rank. And so you can kind of think of this as a charge or a CP operation. You can operate on this by this exchange of the composite fermions, and they transform back to themselves. They're Majorana type with a possible change in sign. In fact, that sign changes. Every time you go up a stairway from one quasi-particle to the next, the sign changes on that. So if you know neutrino physics, you're really interested in that because when you have a Majorana fermions with opposite CP, you package them together to form a Dirac neutrino. That's what you do. So that's kind of interesting. But the particle hole symmetry, however, is missing here. And that's because if you actually do the counting, you find out that it has a half a particle more than it should have to form an exact particle hole symmetry. So that's a really interesting issue to look at. One final thing I'll mention is that there's You can look at another trajectory that's also really interesting, that L equals S minus a half, so that's just on the high density side, one particle higher than we just discussed. That's the wave function that's normally been poorly described by the Fermion. And the Fermion is always this idea that you have an operator that acts on the closed shell state. And this operator is kind of ugly. It's not a simple determinant or anything. So you can ask, can I go ahead and manipulate this wave function into a Fermion-like form, and what does it look like? It turns out you can do that rather easily. Turns out you can write all of these composite fermions as an operator that acts on the closed shell. It's operator gamma. And that operator gamma has a really simple structure. So the gamma for particle I has the appearances of zi squared, and then you start pairing them with aligned pairs, and then you destroy the favorable aligning and make them anti-aligned. So this is what generates the angular momentum. So if I build a 12-particle case for this new Fermion, each of these are vectors, and so this is a 12 by 12 matrix particle types and the different appearances here. Go ahead and evaluate this. It's got an almost perfect overlap with the real wave function. The old Fermion has a really bad overlap. So there's lots of things we're still exploring. This problem is, unfortunately, I'm really jealous of condensed matter. They have so many neat Hamiltonians. We only in nuclear physics we have one lousy Hamiltonian. That's all to deal with. But there's a bunch of things you can do, and we think we can get explicit recursion relation, and this is actually a great use of this hierarchical form. We've been thinking about how you restore particle-hole symmetry. We think it's really important to maintain this LS, this charge symmetry, at the same time restore the particle-hole symmetry. The question is how to do that. One possibility we explored is the torus. We actually think the problem is that in the sphere, the north and south poles are not identified, and that's why you have this breaking of particle-hole symmetry. But there are other possibilities that may be even cuter that may allow you to continue to work on the sphere, but still restore the particle-hole symmetry. There are all these open shell electron cases. What do you do when you go from the 1/3 shell to the 2/5 shell? You start envisioning quasi-fermions partially occupying the shell. How do you form those states? I think we know how to do that. And then I think probably the most interesting question of all is the extension to higher Landau levels, because you can see if you go back through this structure that there's sort of new physics that will show up when you get to higher Landau levels. So this is the publications that we've done. You see that there's this 20-year gap between two papers. I'm really hoping that it's not 20 years. And thank you.
Question.
So what you've been focusing on is the Jane sequences, like 1/3 to 5th, which in the Haldane-Halpern picture would be quasi-electron condensates. You contract your liquid, you take away quanta of angular momentum. How about the opposite thing, quasi-hole condensates, where you add quanta of angular momentum, you make the system more dilute, and then you get the negative Jane sequence? Is that something you can?
The negative Jane sequence. Can you explain what are those feelings?
Feeling greater than
that's where you get
greater than half. Okay.
Yes, the other side.
In our sequence, you just continue, but that is, it generates the entire sequence in exactly this way. So we don't stop at the half-filled shell. We just keep going. So all of them are generated in precisely the same way.
Right. So you go beyond 1/2 and you move your way back, back down the.
So there's some really interesting things. For the hierarchy form has to do with breaking the LS symmetry and basically writing the wave function. If you go back to the original operator for the 2/5 field state, you can write it as d1.d2, d3.d4, the destruction operator, and then times this half-filled shell pair wave function that I wrote down. There's a symmetry between the D's and the U's, and so you can reverse that. And what you find out is you go above the half-filled shell, what you're tempted to do is actually switch notation, so that you can kind of see that the 2/3 filled state must have to do with isolated two-particle systems that have a Laughlin correlation, but with a real tight correlation between them. And that's the structure of this wave function. So there is a reversal. So the way I can explain this is that if you think about this interesting pair correlation that we have in the hierarchy form, where cluster 1 talks to cluster 2, cluster 2 talks to cluster 3, that you can take the interaction of particle 1, trace it through all the other clusters, and come back to where you started from. And then you see you have this interesting topology. You have actually 3 kind of different loops that you can go. You can return to the same particle, return to a different particle, and make another circuit, that sort of thing. So there's also a sort of a two-fluid, or for the 2/5, three-fluid picture, hierarchical picture for these wave functions on the low density side, and then both descriptions on the high density side. And I think the most convenient way to think about the wave function is you switch the definition as you go through nu equal to half. So you're talking about the smallest, you don't want to talk about big density perturbations, you want to talk about the local density perturbations, and those are over densities below the half-filled shell and are under densities above the half-filled shell. So you should make that transformation. We actually haven't worked out the detailed form of that wave function. I'm sure we can do it.
Question, Buck?
So if I understood it right, you had a composite Fermion-like operator where you add the electron in two flux, but one of them gets smeared and the other one stays. And you said you can see the exchange statistics of this kind of object?
You can see that
The exchange, does it look like a fermionic exchange?
it's fermionic. Yeah, it's definitely fermionic. And so it's, I think there's maybe some confusion about the non-interacting form of the wave function, which has these composites in recursion relation. Recursion, you can envision, say in the 2/5 field state, finding an operator that adds 2 particles in 5 flux units. That does take 2 particles in 5 flux units, one of which is associated with the ionic symmetry, so it's 2 with 4. There's a 2/5 field, likewise for the 1/3. So I think there's a little bit of confusion between what you mean by a recursion operator, which really is 1 electron attached to 2 flux units, and with 1 more flux unit forms a scalar, versus the sort of independent particle picture of this that comes from the composite fermions. So definitely 1 flux unit is associated with 1 electron, and then the 2 fluxes are absorbed in the intrinsic wave function, but the other one is distributed and is responsible for the fact that the shell structure evolves as you have particle number.
I just want to make sure I understand. Early on, you introduced these wave functions where you're operating on what you call phi 1/2.
Yep.
Phi 1/2, which says a half-filled shell. This is a Laughlin wave function for bosons.
So you act on using an antisymmetric wave operator and act on the bosonic half-filled shell, and that generates the full sequence of Jane wave functions.
Sorry, I thought there was a single. What did the symbol phi 1/2 mean? That's one wave function, not a whole set of wave functions.
Yeah,
right?
that's the n particle bosonic wave function at the half-filled shell. So Z1 minus Z2 squared summed over.
Yeah, okay, fine. I just wanted to make sure that I understood.
Not
It's a bosonic wave function, not a fermionic.
Yeah, and the operator is antisymmetric, so it has to act on the bosonic wave function.
Okay.
So if you do particle Hall symmetry on the Laughlin state, do you get exactly the 2 folds?
No. So you have to restore that. And again, I think it's connected with these funny boundary conditions on the sphere. I really like to look at this on the torus, but I've invested so much in the sphere. I hate to go back to square one. It's just awkward. If you take, if you form the, say, 2-particle Laughlin state on the sphere, it's kind of think of it as particles, two holes in a particle, but the particle exists at the north and south poles of this cartoon, but has that structure. It's not really, it doesn't have exactly the 1/3 film. And that's, again, you can repair this. For example, one scheme for just trying to restore particle Hall symmetry at the half-filled shell would just take a scalar wave function and break angular momentum symmetry, hit it by one flux unit. So U1, Z1 to Zn line, shifting it left, shifting it right, shifting it all possible ways. That breaks angular momentum symmetry, but winds up can allow you to restore particle Hall symmetry. With these operators, you can always restore particle Hall symmetry if you in this way form the right Hilbert space, because you can just operate them on the closed shell and add the sum of the 2. And there's a way of enforcing particle Hall symmetry. They're really close to being particle Hall symmetry, but they're not exactly.
More questions? If not, then I think we should break for lunchtime. Just remind you that the room will be locked, so you're welcome to leave your gear here if you want, and we'll be back here for the next session starting at 2 o'clock. But let's thank Rick and Rose.